Welcome to lesson number 8 of the neural networks section. In the last video, we simply plotted random distributions of data onto the graph. The goal is to use this data to train and develop an algorithm to come up with a line that best separates data into discrete classes, with minimal error. As you know, a line can be represented by an equation, where W1 and W2, the weights, dictate the slope of the line. These weights start out as random values, and so we're just going to have a random line, which more often than not is not going to classify our data correctly. Clearly this one does not. But as the neural network learns more about what kind of input data it's dealing with, it will adjust the weights based on any output errors that resulted in categorizing the data with the previous weights, until it comes up with a good model. In essence, through every iteration, the network is being trained to come up with a better linear model. And how does it do it? Specifically, how does it know how to adjust the weights? Instead of looking at 200 points, let's simplify our example to 8 points. The blue points are labeled 1, and the red points are also already labeled, but as 0. Now we need a line that best separates this data into two classes. You and I can eyeball this and draw the following line. This line clearly separates all of our data correctly, but the computer can't eyeball it. It has no idea how to start. So what it's going to do is display a random line with some random equation. It's then going to look at this line and identify any errors in categorizing the following datasets. Based on these errors, it's going to eventually adjust the weights of the linear equation to fit the data better. We're essentially training the neural network, but how is it going to do that? Let's go back to our first line. Clearly these 2 points are misclassified. Suppose this is our linear equation. If you take the linear combination of each point, each one would result in a negative score, a value of less than 0. And our step function would then predict each one's value is 0, but this is wrong, since we've initially assigned these points a label of 1, but our linear model predicts their value is 0. The key metric to solving this problem is the error, which tells us if our model is doing well or not, depending on how large or how small the error is. And now, through gradient descent, our network is going to take tiny steps to reduce this error in every iteration. These tiny steps correspond to the learning rate, which needs to be sufficiently small, since when the line is fixing itself, you never want it to move drastically in one direction, especially when you have a lot of points. At every step, the line will move closer to the misclassified points, and it keeps doing so until there are no errors, or until the error is sufficiently small, and by doing so, we eventually obtain the perfect linear model. Suppose the perfect linear model for this set of data was defined by the following equation. We can now conclude that in classifying our data, our linear model clearly gives more weight to x2 rather than x1. The main theme of this lesson being, the algorithm starts with a random line defined by random weights. The neural network, as it calculates the errors, it starts to learn more about the input data. It then readjusts the weights to minimize these errors and thus better classify our data. How does it calculate the error? How do we determine which points have the largest error relative to the current linear model? Well, before getting to that, we need to reshape our view on the perceptron model. Let's talk about that in the next lesson.